Swayamprabha. Digital India. Educated India.
Greetings and welcome again to this course on CFD. Last class we had seen deriving governing equation, Reynolds test, modeling strategy. In particular, we came to know about standard models, standard K epsilon and standard K omega model. We also listed different proposals available in the literature in standard K epsilon and standard K omega model to improve the performance. One such proposal was low RE model, and in today's class we are particularly going to see about low RE model. Before going to the detail, I would like to present what is known as a boundary layer, and what is shown here is a flat plate. Flow is coming from left to right with a uniform velocity condition u infinity, and this is a leading edge. Flow develops over the flat plate. Initially you have a flow laminar, then there is a transition point, then you have a turbulent boundary layer. So, turbulent boundary layer has three main regions. One is viscous sublayer as marked here, then buffer layer, then log layer, and boundary layer thickness is given by a symbol delta, and boundary layer is defined as velocity which is equivalent to 99% of free stream velocity or the incoming velocity 0.99 of u. So, boundary layer is a thin region near the surface in which velocity changes from 0 at the surface as shown here to the free stream value as shown here. So, this may be either laminar boundary layer or turbulent boundary layer depending on Reynolds number. Now, in this case the Reynolds number, we use velocity as an incoming velocity, and the length scale is a distance from the leading edge. Obviously, if you are very close to the leading edge, the Reynolds number is small, and if you go very far, the Reynolds number is high, the flow actually becomes turbulent. We have seen now flow past a flat plate with the different regions, that is laminar, transition and turbulent region. In the turbulent region, we have further sub details. We have three different layers: viscous sublayer, buffer layer and then log layer. So, in the next slide I am going to explain in detail about these three different regions in a turbulent boundary layer. Before going to the details, we should first know what is known as a scaling. Scaling the variables near the wall, we have length scale and then velocity scale. In the velocity scale, we have shear velocity u tau defined. U and tau is for friction or shear velocity, and that is used to scale velocity, and distance from the wall is given as y, and nu is molecular viscosity. So, we define non-dimensionalized velocity u bar, that is a mean velocity, and because it is non-dimensionalized we use superscript plus. So, u bar plus equal to u bar by the velocity scale that is used to non-dimensionalize, that is u tau. U bar by u tau is actually u bar plus. Similarly, you can also non-dimensionalize the distance. So, if you non-dimensionalize the distance, it becomes y plus. So, it is a non-dimensionalized wall normal distance. So, actual distance is y, we use u tau as a velocity scale and nu is molecular viscosity. So, if you put them together, you get non-dimensionalized wall normal distance, which is written as y plus. So, in this plot we have horizontal axis which is given in logarithmic scale, and vertical axis which is defined the usual linear scale. So, this plot is a semi log plot. On one side we have a linear scale, on the other side we have a logarithmic scale. We have multiple curves with the different color. We will explain each one of this very carefully. The first one is you have a dashed line which is shown in the green color, and you have the actual profile running as shown in blue color. Okay. This blue color is actual velocity profile. Then we have one green color curve which is superimposing over the actual profile for some distance from the wall all the way up to some value of y plus. So, when you say y plus is plotted on the x axis, so this becomes wall, that is y plus equal to 0, and this green color is an empirical relationship, and that is given by the relationship as u bar plus equal to y plus. So, this green color line is an empirical relationship, and that is a linear relationship. Because we are using semi log plot, it appears as a curve. Then the next zone is buffer zone. We will not talk about it right now. We have the log region, the third zone is a log region, and the expression for the log region is given here, that is u bar plus equal to 1 over kappa ln y plus b. Kappa is a constant which is given a value 0.41, and b is another constant which is given a value 5.5. And this expression, as you can observe, is a semi log expression, because on one side you have a straight value, on the other side you have a logarithmic expression. And on this semi log plot, this kind of expression will appear like a straight line, and that is what is this region, which is marked as a red color. So, this red color straight line that is appearing is actually representing this logarithmic expression. So, the actual profile, which is blue color, is partly coinciding with the red color for some part of y plus. You can observe here, it is coinciding with the red color from this value of y plus to this value of y plus. So, then the actual profile deviates from that expression. Now, between this linear region where the actual velocity profile coincides with the green color line. So, that is a linear region. The another region is a log region, that is somewhere here. In between you have a region that is what is known as a buffer region. So, we have a 3 region starting from the wall, linear region, it is otherwise called viscous sublayer region, buffer region which is in between, then we have a log law region where we have a semi log expression relating velocity and wall normal distance as shown here. After some point of y plus, it is deviating from the logarithmic expression. So, this plot is very special, because we are using non-dimensionalized velocity and non-dimensionalized wall normal distance. It is special because it is universal, whatever the type of flow, because we are normalizing with respect to shear velocity u tau and with respect to viscosity, this plot becomes universal, and that is a speciality of this plot. Scaling the non-dimensional velocity and non-dimensional distance from the wall will result in a predictable boundary layer profile for wide range of flows. Because we are using respective u tau and respective nu, and we already learned it is possible to split the actual velocity profile into 3 zones: linear velocity profile or viscous sublayer region, buffer layer, logarithmic layer, and there is a specific expression available for 2 zones, and for outside the log layer it is possible to predict velocity profile near the wall. Since the near wall conditions are often predictable, functions can be used to determine near wall profiles, and these functions are called wall functions. The wall functions are used to bridge the gap between wall and the first nodal point. We are going to see in the next slide some details about it. Important point from this plot is this plot is universal, which means it is applicable for wide range of flows, because for different flows you get different u bar and u tau, but you can non dimensionalize and they all fall in the same plot. Y plus is a non dimensional distance from the wall, as we said before, and it is used to measure the distance from the first node away from the wall. Not necessarily, it is used for other points as well. Now, here is the description. The shaded portion is a wall and these are all mesh. Horizontal lines, horizontal thick lines and vertical thick lines are supposed to be the mesh, and here is a boundary layer profile. If you happen to have a first node that is shown here as a yellow circle, that is the first node, for example, in your computation from the wall, then that will give you the y plus of the first node. Wall functions are only valid within specific y plus values. If y plus is too high, that is if you happen to have first point somewhere here instead of here, or if you happen to have the first point little far away from this point, okay, or it is very far from the wall, then the first computational node is near the edge of the boundary layer and wall function will be imposed too far into the domain. Near wall physics is not captured, predicted or not accounted properly. If y plus value is too low, that is you are very close to the wall, then the first computational node will lie in the laminar or viscous part of the boundary layer, where wall functions are not valid. Now, at this point again I would like to remind the equation we derived, mean momentum equation. In the mean momentum equation, we had 3 terms on the right hand side, first term for the pressure, second term for the laminar stress and third term for the turbulent stress. Depending on the contribution of the laminar stress and turbulent stress, then y plus will have the influence. So, if y plus is very close to the wall, then we have the laminar viscosity playing role, there wall function is not suitable. If the y plus is very far, then you are actually outside the boundary layer, there also will not have any influence. Fewer nodes are needed normal to the wall when all functions are used. So, you can use for points defined as shown here very close, and you can relate physics at this point with the wall or the region between first point and the wall. The physics associated with the region is represented by what is known as a wall function. If you happen to have a luxury of very fine mesh near wall as shown here, then wall function cannot be used, because you are able to integrate all through the wall layer up to the point on the wall. So, prediction of near wall phenomena, for example, you are interested in skin friction coefficient or any wall normal velocity gradient, Nusselt number depends on mesh resolution near the wall. So, very near wall local RE is very low, and again the laminar stress refer to the Reynolds average Navier-Stokes equation. You have terms corresponding to laminar stress and term corresponds to turbulent stress. So, laminar stress plays role higher than turbulent stress. If the mesh near wall, the near wall mesh is fine enough, then wall function approach is not valid as shown in the figure in the previous slide. You have alternative, one you can go for 2 layer approach, other one you can go for low RE models. So, in 2 layer modeling approach, region very close to the near wall is solved separately, either empirically or by following one equation model or any other relationship. And away from that region at some specific wall normal distance, you can use any one of the standard models or their variants. If you are very near and their local RE is very low, then damping function is introduced, which damps the turbulent viscosity depending on wall normal distance. I am showing here list of low RE two equation model available or proposed in the literature. For every category, for example, k epsilon model, k omega model, you have list of proposal. I am going to show only a general format of the low RE model and then one or two variants of the low RE model. So, general format you have here again for k epsilon type turbulence model, you have equation for k and you have equation for epsilon. The difference you will notice particularly nu t in standard turbulence model is C mu k squared over epsilon, and we introduce a damping function called f mu. F mu is a function which damps the turbulent viscosity very near the wall. In other words, laminar viscosity will start playing a dominant role. In this expression, we have different definition of Reynolds number RET, RY and Y plus. Y plus is one, Y plus we define as a wall normal distance u tau y by nu. It is also Reynolds number as I mentioned before. Similarly, Ry is also a Reynolds number. If you look at the expression root k y by nu, k we know is a turbulent kinetic energy, the unit is meter square per second squared, and if you take a square root that will give you velocity scale. So, velocity scale distance divided by nu is actually Reynolds number. Similarly, you can define another Reynolds number. So, this is called turbulent Reynolds number, getting a Reynolds number based on k and epsilon, and this is based on absolute distance and another one based on wall normal normalized distance. So, different proposal that are listed in the table, the difference here is only the way functions are expressed and how different constants are obtained. So, Jones and Launder is one such proposal somewhere around 1972, an expression for this is available. Similarly, the another proposal Launder and Sharma, again expression for function and different quantities are available here along with prescribed boundary condition. These are all well documented in the literature, available in all standard books, and it is difficult to go through all the derivation in detail in this class. Another important aspect is whether we can have some idea of y plus before starting the calculation. We mentioned y plus is a factor where you decide whether you want to have a wall function or you want to have a two layer approach or whether you can go for a low RE model. So, it is obviously beneficial if you know some idea about y plus before starting the solution, and that saves lot of time. Some empirical formula is available. For example, what is listed here is for a flow over a flat plate, delta y is a first normal distance from the wall. So, delta y equal to L y plus square root of 74 R e L to the power of minus 13 by 14. Now, this will decide if you fix your y plus, for example, you want to have first y plus value as 5, then using this expression you can get delta y, and delta y is the distance from the wall of the first node. Just like we have boundary conditions for primary variable u, v, w and pressure, turbulence equations k and epsilon also require boundary conditions. and several options exist for specification of turbulent quantities, mostly at inlet, and we follow a similar expression at other locations. Unless turbulence is being directly simulated, that is, there is a class of turbulence simulation called direct numerical simulation, where there is no modeling approach. Navier-Stokes equation and continuity equation is solved as they are available. The interpretation of the variable is each one of them represent instantaneous quantity. If you happen to use the instantaneous Navier-Stokes and continuity equation as they are, then you are actually doing direct numerical simulation. You have only 3 or 4 variables, 3 velocity component and 1 pressure component. We prescribe boundary condition for them, and there is no need for knowing about boundary condition for k and epsilon. There is another point, what is known as a intensity, turbulence intensity, and that is shown here. Intensity is I u RMS by u bar, where u RMS equal to square root of u1 prime squared plus u2 prime squared plus u3 prime square, and you take a square root, that will give you the intensity. So, intensity normally is given either in experiment or appropriate condition. If it is not given, then one can take the value between 3% to 5%. In addition to intensity, one also needs to specify length scale, and from both you can get kinetic energy estimate at the inlet, and results are very sensitive to the specification of this k, epsilon, omega at these boundary condition location. So, in this week we had seen important topic, introduction to turbulent force, deriving governing equation for turbulent flows, what is known as Reynolds stress and how to close Reynolds stress term appearing in the mean momentum equation, introduction to standard models, different variants of the standard models and explanation associated with them. We also learned a little bit about what is known as a low RE models, and then some information about boundary condition. With this, I close class for this week. Thank you very much. We will see you next week. Until then, have fun.